Let's be honest, naming organic molecules can feel a little complicated. You see these long, crazy names and think, how could anyone possibly remember all that? But what if I told you there's a beautiful, hidden logic to it all? Today, we're going to crack that code. So here's what we're going to tackle. We'll start with a group called anhydrides, then we'll jump into ring-shaped or cyclic compounds. After that, we'll figure out what happens when things get crowded and you have to decide which part is the real main chain. And we'll wrap it all up with a really cool, elegant shortcut for molecules with double bonds. Let's dive in.
First up, let's talk about a family of compounds called anhydrides. Now, don't let the name intimidate you. You'll see that the logic behind how we name them is actually super intuitive.
So here's the one thing you really got to remember. An anhydride is basically what you get when two acid molecules get smushed together and a water molecule gets kicked out. If you can just keep that one idea in your head, the naming part pretty much solves itself.
This slide just lays it out so perfectly. Check it out. If the two acid pieces that came together are exactly the same, like two ethanoic acids, you just say the name once. Ethanoic anhydride. You don't need to say diethanoic or anything because it's implied. But if the two sides are different, like one ethanoic and one propanoic, you just name both of them, and you put them in alphabetical order. That's it.
All right, let's switch gears and talk about a new shape. Cyclic compounds. These are molecules that literally bite their own tail to form a ring. And just like before, there's a really clear pattern to how they get their names.
Okay, the basic idea here is super simple. You already know that a 3-carbon chain is called propane. Well, if you connect the ends of that chain to make a little triangle, a ring, what do you call it? Cyclopropane. You just stick the prefix cyclo right on the front.
So what if we hang a little methyl group off of it? Well, think about it. Does it matter which corner of the triangle we put it on? Nope. It's the same molecule no matter what. It's always going to be considered carbon number 1. So because of that, we don't even need to bother writing the number in the name.
But this is where things get really interesting. What happens when that chain we attached starts to get bigger and bigger? At some point, we have to ask a really important question. Which one is in charge? The ring or the chain?
Let's look at this power struggle. As long as the side chain has fewer carbons than the ring is the boss. It's the parent name. Even if they're the same size, a 3-carbon ring and a 3-carbon chain, a tie, the ring still wins. But the very second that side chain gets 1 carbon longer, everything flips on its head.
So here it is, the moment of truth. We've got our little 3-carbon ring, but it's attached to a 4-carbon chain. The chain is now officially longer. So who's the main character in this story? And here's the answer. The chain takes over. That longer 4-carbon chain becomes our new parent molecule, butane. And the ring? Well, it gets demoted. It's now just a cyclopropyl group hanging off the side, like any other substituent.
All right, let's up the complexity just a little bit. What happens when you have a bunch of different things all attached to the same ring? How on earth do you decide where to start counting?
Well, if you don't have any super important, high-priority functional groups on there, it all comes down to a simple tiebreaker, the alphabet. You just look at your groups, chloro, methyl, nitro, and you start counting at the one that comes first alphabetically. In this case, C for chloro wins, so it gets to be number 1.
Now this slide is so important because it shows the exception. On the left, we just followed the alphabet. But look at the right. We've introduced an alcohol group, that negative OH. An alcohol group is like a VIP. It doesn't care about the alphabet. It walks right in and takes the number 1 spot on the ring, period. Everything else just has to number around it.
All right, for our last major rule, we're going to look at something that is honestly just so clever and efficient. It's the special rule for naming rings that have a double bond in them. Okay, so there are a few things that are totally non-negotiable here. First, the 2 carbons in that double bond have to be numbered 1 and 2. No exceptions. Your only decision is which way you count, which carbon is 1 and which is 2, and you make that choice to give all the other groups on the ring the smallest possible numbers. And to make this rule really stick, the lecture this is based on had this fantastic analogy about making a local phone call.
And it makes perfect sense, right? When you're calling someone in your own country, you don't dial the country code. Everybody just knows where you are. It's the same idea here. The rules require the double bond to start at position 1, so why would we waste our time writing -1 in the name? It's completely redundant. That's why we just say cyclohexene, and that one is totally understood.
Okay, time for the final boss. Let's take everything we've just learned and try to name this beast of a molecule. It's got a ring, it's got a high priority group, it's got a chain hanging off it, and that chain has its all thing hanging off of it. Let's do this. The only way to tackle something like this is to not panic and just go step by step. First, find the most important part, the VIP. That's the ketone, the double-bonded oxygen. That makes the parent a cyclohexanone, and that ketone carbon is number 1. Easy. Next, we number the ring to give that big branch the lowest number, so it's on carbon 2. Now we just focus on the branch itself. It's a 4-carbon chain, so it's a butyl group, and on its second carbon, there's a chlorine. So the branch's full name is 2-chlorobutyl. We wrap that in parentheses and put it all together. Done.
So you see, that name that looks like a total mess at first is actually a perfectly logical set of instructions. It's a map, and now you know how to read it. So the next time you see one of those long, scary chemical names, don't get intimidated. Just take a breath, break it down, and see if you can spot the beautiful, hidden logic inside.